Hey everybody, this is Larry. This is day 20 of the Leetcode September decoding challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know how you're doing. And yeah, today's problem is unique paths 3. Okay. So return the number of 4 directional walks that works any non-obstacle square exactly once. Okay, I think the big thing to notice is the first thing I look when I see these kind of problems, and some of this is experience, is kind of figure out, well, when you have to count the number of paths, it's either, generally speaking, it's either dynamic programming or backtracking, or maybe some sort of decomposition of the problem into components that you can do multiplication on, right? The product of components or something like that. But those are the levels that I would think about. But for this one, why is it not a dynamic programming problem, right? Well, the reason why it's not a dynamic programming problem is that we don't have a DAG, and a common version of this problem does give you a DAG as an input, and the reason why that is because you're able to only go down and right or down and left or something like that, right? Where basically you cannot go backwards, and therefore there is a directed asynchronous graph where you could represent. It's basically there's no cycles. You can go on a graph, but in this one there are clearly cycles, right? There's like you go from 1, you just do a loop, and then that would be wrong, right? So definitely because of that, I don't think there's a or not. If there's a dynamic programming solution, it's not a direct dynamic programming solution, right? So I think the second thing I noticed from that is that I look at the constraints, and the constraints sometimes it's a little bit you have to pay attention. I think sometimes it's easy to look at, n is equal to 20, so this is whatever. But it turns out that this is actually rows times columns is equal to 20, meaning the number of cells would be at most 20. From that, well, you can probably do backtracking, because there's probably some self pruning property to this that you could do backtracking, and some optimization noticing that it is 20, so you can probably use some sort of bit mask if you have to optimize that down if needed. And also in theory, you guys would do the n times 2 to the n dynamic programming if you need, based on the fact that it's 20. But that's kind of where my mind is landing at. So first, I actually don't remember I don't know how which way is the preferred way. So I'm going to just start with backtracking. So let's set that up. So backtracking, we start with 1 and then we go to site 2. Okay, let's go. So okay, so let's go. Rows is equal to length of grid. Let's set that up. Columns is equal to length of the first row. Hope that's the same. They actually should tell you whether they're all the same just to be sure, but if it doesn't, then we'll play around with it later. And then let's find out the starting. You got starting XY and also ending XY. This is just my convention usually. Yeah, and right now we're just going through the matrix to set up our inputs. Then Sx is equal to X, or y is equal to XY, and also we change it to 0 just because maybe, I don't know yet, but it may make our base case a little bit easier, because then we don't have to additional cases with it, and that's just, and we have to ask why. It's just most experience, to be honest. So yeah, and then now we're just going to do a classic backtracking. Let's set up a global-ish thing with paths, and then we return paths. And also, I think one thing to note is that given that there are 20 cells, a very naive interpretation is that there are 20 factorial ways to do backtracking, but because you're constrained with only 4 neighbors, it's probably way less. I am not good enough in math to tell you what it is. I just right off my head, but definitely play around with that as an exercise if you like. But yeah, So now let's go ahead and go backtrack. Let's say we're currently at let's just get current x, current y, and x and y, and yeah, how do I want to do this? Yeah, so basically, I'm just thinking about what is the best way to check that you've been to every cell, and you could there are a couple ways you can do that. I think you can, for example, what I talked about with noticing that this is at most 20, so you could do a bit mask to kind of hash a set of what you've seen before. And I think that should be okay. So let's do it that way. Let's just have a scene array or scene set. You can actually probably get a little bit more clever with the depth of the search tree, and just count the number of zeros or something like that. But I'm just gonna be a little bit lazy. But I guess it's the same thing, to be honest. But from that we have to count the number of zeros. So let's just do spaces is equal to 0, and then now this is after we modified the above. So now if it is 0, spaces increment, and the thing is that basically is just that we take out the obstacles, so that if we've seen enough, then that's okay, right? Yeah. Okay. So now, yeah, if cx is equal to ex, and cy is equal to ui, you can write this in a couple of ways. Then, yeah, and length of the scene is equal to spaces, then paths increment. Yay! Oops. And then we return because why bother? Otherwise, and let me just set up the directions here. So I do get questioned about how this works for direction, but I always write it the same way, so it doesn't same way ish. So for 4 directions, you can look at this as the first element is dx, and this is as dy, and basically this is saying, okay, this is going, dx positive, depending on how you want to define your x's. So I guess dx positive is down. This goes to the right, this goes to up, and this goes to the left, right? So those are the directions, and I do this commonly, and many people, competitive people, write it in a similar way. And yes, and then I can write something like for dx, dy in directions. And then my notation is nx ny for the next x next y. Again, it doesn't really matter that much, as long as you're consistent enough that you do it every time, then you don't confuse yourself, right? So basically, you want to go from cx plus dx, cy plus dy, and then you just have to check the bounds, meaning if nx is between 0 and rows, and y is between the rows and columns, and grid of nx and y is equal to 0. Okay, what happens here, right? Well, oh, and I guess I have to do one more. Oops, how did that happen? And we haven't seen it yet, right? And that's just nx and y not in scene, right? Then it's just standard backtracking. Is we put it in scene, and then we backtrack. The current xy is the new xy, and then we just go exy, scene, yeah, and then we remove it from afterwards as the backtrack, and I think this should be mostly good. Yeah, let's give it well, we have to kick it off. I always forget to kick it off. So we backtrack from the starting, and yeah, new set. Though I should put some of this doesn't need to kind of pass on every function. That kind of adds up sometimes, but maybe it's okay. So 0 is probably not good, but in the meanwhile, let me put in the test cases while I'm here so that I don't do it later. I wish they have a button for that, but that's besides the point. Okay, well, at least we're consistent. Oh, I have to do non-local, that's why. Well, I mean, that's one of the reasons why. There might be other reasons, we'll see. That No, I don't. It doesn't complain, so maybe it just doesn't get here at all. Oh, I don't. I don't add the first element, so it's probably maybe off by 1. Hopefully that's it. Oh, whoops. Okay, well that's awkward. Am I missing something obvious? Probably. Well, the good thing is that it is you can see the tree very easily by, well, okay, this is the one that had, by just putting out the stack traces, cx, cy, ex, cy. I think I also want to do this maybe a different way. Yeah, maybe I'm locking it in a different way, but okay, so it started at 0, 0. This seems good so far, but it's just that we never deal with this. Did I miss this somewhere? It just seems like I didn't parse correctly the EXEY. Did I miss this up? Well, at least that's a easier fix conceptually. That's odd, right? I mean, that's just 2 for loops, so I didn't really get a sense that that would be it. Am I going nuts here? That looks good, but and then we do convert it, but why is it that we don't? Oh, there's an extra. That is a little sad actually. Okay. Okay. Sometimes that typo. That's why I was like, I guess it's easy to kind of have typos. Okay, let's again put these test cases back in. Yeah. Okay, and then now I want to test just like a really basic case, and also just a really big case. I guess 5 times 4 is probably okay, right? Because you do want to see how it performs over over stressful situations. So let's just go upper left, upper to lower right, and then see the timing on it. I thought it is. Oh, I did an extra one because my math sucks. But okay, so that looks good, and also only 20 paths is a little bit surprising, maybe, but maybe not. I don't know. Let's see. Like I said, it is a lot of self-constraintion, and it seems pretty fast, so it's ready to go. Let's give it a go, and yay, accept it. So with backtracking, it's always a little bit tough to get the exact complexity. The branching function for each one is going to be 4, but there is a lot of self-constraints and restrictions. So yeah. But this otherwise is a good basic backtracking problem. Definitely, support being comfortable about it. The idea behind backtracking is that every time you go down, you change the state, and then you also reset the state afterwards. And that's what I did here. The only thing I had was a minor typo here, which, okay. Yeah, cool. That's all I have for this problem. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord, and I will see y'all tomorrow. Bye bye.